In traditional Byzantine fault-tolerant blockchain design, there is a strict operational paradox. Adding more hardware to the network actively decreases its total throughput. The root cause of this limitation is Amdahl's law. This computational principle dictates that a system's potential for parallel speedup is strictly limited by its sequential bottleneck. Traditional distributed ledgers require every node to synchronize the global state sequentially. In mathematical terms, this creates a high sequential bottleneck, meaning the system operates with an S value significantly greater than 0. Because block production typically relies on a single leader node, every other node on the network must wait its turn and coordinate conflict detection at runtime. The engineering alternative is an S=0 architecture. In this model, execution occurs in parallel, which aims to remove coordination overhead from the runtime path. Achieving linear scaling requires moving global synchronization out of the transaction execution path, shifting toward a decentralized network topology. SynapticChain draws its architectural structure from biological neural networks, mapping those concepts onto a rigid graph-theoretic framework. In this system, nodes operate as validators, acting as individual neurons, while the trust relationships between them form weighted connections, operating as synapses. Pure proof-of-stake systems derive network influence from capital alone. This leaves the network vulnerable to immediate Sybil attacks by heavily capitalized actors. To solve this, the network calculates a synaptic weight vector. Stake constitutes 50%, while reputation at 30% and uptime at 20% act as throttles. This restrains a newly capitalized malicious node until it proves long-term reliability. By intertwining capital with time-tested behavior, the system ensures that network control must be proven over time. It cannot simply be bought. To understand how SynapticChain achieves sub-500 millisecond finality, we have to break down its decoupled four-phase execution pipeline. Phase 1 is transaction submission. Clients submit transactions to the network, which then must assign those inputs to processing lanes without relying on a global coordinator. The network utilizes deterministic routing by applying a hash function directly to the sender's address. This address hash mathematically maps the transaction to a specific 3-node localized cluster, known as a shard. Phase 2 is shard consensus. Inside the isolated shard, the 3 validators verify cryptographic signatures and token balances. The network uses compile-time static scheduling. Because dependency checks occur before execution begins, runtime conflicts are prevented. This static scheduling means multiple transactions assigned to the same shard process simultaneously in parallel lanes. Approval requires meeting a local activation threshold. A transaction is only verified when validators representing 67% of the shard's total synaptic weight sign it. This 67% threshold vote occurs concurrently across hundreds of completely isolated shards. By mathematically confining execution and validation to local 3-node clusters, phases 1 and 2 bypass global coordination during the execution phase, satisfying the S=0 architectural design. This creates an architectural challenge. How do these independently operating shards synchronize back to a global state without transferring massive amounts of raw transaction data? Phase 3 is cross-shard coordination. Instead of broadcasting full transaction payloads across the network, each shard computes a localized Merkle root hash, a cryptographic summary of their approved transactions. These local roots are then transmitted to a central mesh aggregator. The mesh aggregator verifies that local state transitions match across connecting nodes, ensuring cross-shard validity without data bloat. This leads to Phase 4, checkpoint finalization. The protocol utilizes a directed acyclic graph consensus model. Multiple validators produce and sign blocks simultaneously, operating without a single leader. The aggregated checkpoint is locked only when 67% of the entire network's synaptic weight signs off. This final, irreversible global checkpoint is written to NVMe-backed storage every 500 milliseconds. Global state synchronization is transformed from an ongoing sequential bottleneck into a periodic, low-bandwidth cryptographic summary, powering the sub-500 millisecond finality engine. The mathematical limits of this design define the SynapticChain Byzantine fault-tolerant classification, or SCBFT. The network continues to operate securely as long as up to 33% of the total synaptic weight acts maliciously. In a network partition scenario, where an attacker attempts to double spend or spoof an invalid state route, their wait stalls, mathematically incapable of reaching the 67% threshold. The protocol executes programmatic slashing responses, penalizing 10% of total stake. Submitting an invalid state route triggers a 20% slash and immediate ejection from the validator set. The protocol computationally isolates and economically destroys malicious actors faster than they can manipulate the global state. The theoretical architecture is supported by empirical data gathered during the April 2026 burst test on the production testnet. A single shard processed 400 unique transactions in 154 milliseconds. This resulted in a sustained single shard throughput of 1,084 transactions per second. This benchmark supports the S=0 model. By removing sequential dependencies from the execution path, speedup scales with the lane count, tempered only by a constant network overhead factor. This creates an exact linear extrapolation formula, adding 3 nodes to the network. Mathematically, moving from 3 validators to 1,000 validators pushes the network from 1,000 transactions per second to over 360,000. While traditional designs suffer from diminishing returns as validator counts rise, SynapticChain's use of deterministic sharding and DAG checkpointing allows execution throughput to scale linearly with network participation.